Okay, so we built up this ramp. The last talk was half ML, half Rust, and this one is now full Rust by Aaron.
Hi everybody, I'm Weiss, and today we're going to talk about some ongoing work I've been doing with Daniel Patterson and Amal Ahmed on distilling the essence of Rust. Actually, you can see Daniel. Before we do that, let's actually talk a little bit about what Rust is and why it's interesting. I know you just heard us about that, but we're going to talk more. So first, Rust is a systems language, meaning that it provides low-level abstractions for dealing with memory. Rust is also a fast language, and to do this, it relies on what they call zero-cost abstractions that they use to ensure that idiomatic Rust code is as fast as possible. And finally, Rust is a safe language, or at least ideally it's a safe language, in that it statically prevents a variety of memory and concurrency-related bugs, such as seg faults and data races. Rust also has a bunch of neat marketing slogans of the form X without Y, or good without bad. Each of these captures some aspect of the language that makes it somehow special. The most important of which is, of course, to hack without fear. Finally, and perhaps most importantly, Rust is interesting because we have cute credits. This is Ferret, the official mascot of Rust. With all that good and none of the bad, the natural question to ask is, how the heck do they do it? It seems like a lot, right? So the answer comes in the form of two related and intertwined concepts, ownership and borrowing. With ownership, we say loosely that an identifier owns the value bound to it, meaning that it somehow belongs there. Then with borrowing, we can say that new references borrow the value for some time and return the value to where they belong when they drop out of scope. Please note that if you're unfamiliar with Rust, this ampersand down there is denoting the operator make reference. So with that in mind, let's look at a real Rust program to see both of these concepts in action. So here, we have a small asynchronous program in Rust that uses the IRC code, an open source library that I've been maintaining since I first started programming Rust in 2014. To help walk through our example, we have Ferris here to help out by moving along with the code as I speak. So, in our example, we create an asynchronous runtime called Reactor. We use it to create a new IRC client connection based on a configuration, and then identify with the server on the other end. Afterward, we actually register a closure to use to handle new incoming messages from the server. In this case, simply by printing them out. And then we run the reactor, which causes the program to block indefinitely as it processes new messages as they come from the server. Now, you can see that here, we actually borrow a config in order to create the client. This allows us to later in the program make use of the configuration. We don't do it here. In principle, we're still allowed to continue using the configuration. By contrast, here we've actually moved the client into the reactor when we register it with this handler, which is actually important because it prevents us from later introducing concurrency-related bugs like data races by using the client from another thread while the reactor is running. Now, I hope at this point we can all have sort of a rough idea of how Rust works. But as a semanticist, I actually want to have a more deep understanding. And to do that, we, of course, need some Greek. But before we get to any of that, I actually want to talk a little bit about what we currently have to help us understand Rust and how it works. We, of course, have its primary implementation from Mozilla and many other open source contributors, Rust-C, which features ownership and borrow checking implemented via an interprocedural static analysis. That's really built on piles of these homegrown, organic, really ad hoc constraint solving that has really developed over the years to sort of meet the demands of new programs that people want to run. Unfortunately, this natural evolution of code, while practical for implementing, is not very good for sort of reading to get a deep understanding of what the invariants are, what the rules are. And the actual implementation has a lot of bugs and inconsistencies around sort of the very edge cases of Rust. More recently, From Populate 2018, we also have Rust Belt, a formal language from Ralph Young, Jacques-Henri Jourdan, Robert Krebers, and Derek Dreyer, which they have specified in the Iris proof assistant. Unfortunately for us, it falls short of being a semantics for source Rust, since it's in a CPS style and corresponds roughly to MIR, an intermediate representation used by the Rust compiler. We want to build a higher level semantics, and so we've been working on one we call Oxide, which we'll explore throughout the rest of this talk. As a quick aside, the black mineral you see here is hematite, which the chem nerds in the audience might recognize as the mineral form of iron oxide. Now, to start, we'll explore the underlying core concepts of Oxide, and then take a deeper dive into our approach to type checking. The first key concept is the idea of using capabilities to model ownership. That is, for each identifier, we'll associate with it a capability that guards its use. Then, to model borrowing, we'll allow our capabilities to be split into fractions. In the case of an immutable borrow, we'll split the capability in half and associate one piece with a borrow, leaving the other half in place. You'll note that we left a blank space to remember that some part of the capability is missing. Then, in the case of the immutable borrow, we'll actually move the whole capability, but again, leave the same blank space to denote that the capability is missing. When we actually drop a borrow, we use this space to return the capability to its original location. That's a good talk. There's also another kind of change of ownership called a move, which models a permanent transfer of ownership from one place to another. In this case, we actually move the capability to the new identifier, but forget its origin, preventing us from ever using the old identifier. So at this point, we've now seen how capabilities can be used to model ownership, borrowing, and moves. As a point of terminology, we're actually going to call these borrows, like the ones we just saw conceptually, loans. You can see right here, we've highlighted the part of the borrow in the original program we were looking at, and we're calling it a loan. So with that in mind, let's talk about lifetimes, or as we prefer to call them here, regions. Regions appear in reference types, as we saw in this talk, and give us some understanding of how we can use the references. So for example, if we have an identifier, X of type U32, which is the 32-bit unsigned integer type, we can make a reference at type and tick X U32. And this tick X is actually naming an abstract region for the reference, or in Rust's normal terminology, a lifetime. And in order to keep type checking tractable, we actually understand each of these regions as corresponding to a set of loans in the program that must all be valid in order for the use of the reference at this type to be valid. Thus, if any of the corresponding loans for tick X were invalid, we would not be able to use this value. If this is unclear right now, please don't fret. In just a minute, we'll take a closer look at typing judgment, and that might help add some clarity. So with that being said, and with regions and ownership both covered at a high level, we want to take a deeper dive into exploring our type checking judgment by looking at its forms and two hopefully illustrative rules that sort of capture the core parts of those semantics. So we'll start with the form, which itself starts with a global context sigma that contains the definitions of user-defined types used in the program. So this is like struct definitions, type aliases, you could have, we currently don't, but you could have like top-level function definitions in this environment. It's relatively standard. Then we have the type variable context delta that contains all of the in-scope type variables and associates them with their respective kinds. In our type system, we only have two kinds, type and region. Then we have variable context gamma, which associates identifiers with their type, as well as a capability that guards their use. So we represent these capabilities actually using fractions ranging inclusively from 0 to 1, which allows us to do the splitting that we saw earlier. Then we have a loan context L, which contains all of the valid loans and associates them with both the capability they took and the place that they took the capability from. Finally, we have our last context, rho, which maps region variables, like the tick X we saw, to a set of loans, which, if invalidated, would invalidate the whole region. And yeah, I know there's a lot of context. So then, in all of these contexts, we check the expression E and get back a type tau, and in effect denoting the impact that type checking this expression had on ownership. Currently, our set of effects is actually very simple and really only allows us to record creating new loans via a borrow or dropping an existing loan. So now we'll take a look at the typing rule for borrows. You might notice here that the first two contexts are grayed out, although the projector looks a little bit blue, so I guess they're blued out. So they're grayed out or blued out because they're not particularly relevant to these rules. So here we're going to type check an expression of the form and today x. This is a little bit of a departure from standard Rust syntax because normally when you write an expression for reference, you don't have the today. And we actually are using this to actually give a name. We're letting the programmer or compiler give a name to that particular loan set. Yeah, and you should also notice that in gamma we've said that x has to be bound with some type and some fraction. Now, before we can actually give this reference a type, we have to require that this fraction be non-zero. Because if it was 0, that means that there was a mutable borrow that happened, and then it's not safe to create new immutable borrows because we might have data races. In the case of a mutable borrow, this would instead have to require that the fraction be 1, because that would mean that there was currently existing, if it was not 1 but not 0, it would mean there was currently existing immutable references. So then we can finally give the type to the reference and set of tick A 10. And so in this case, we're actually giving a concrete region rather than a variable region as we saw earlier. And really the most notable difference is just that this set is a concrete set of regions, and when we'll type check later, we'll actually combine the sets together to add more regions, which you wouldn't see in the types in types with a variable region. Okay. And finally, we can yield a borrow effect that indicates that we're creating a new immutable loan called tick A and borrow for x. Now we're going to look at a slightly more complicated rule, branching. And again, we've glued out the two first contexts because they're not relevant in these rules. So in this case, we're type checking an expression, the form if E1, then E2, else E3. So first, we'll type check E1 and get out the type bool and in effect epsilon 1. Then we'll apply the effect epsilon 1 to gamma, L, and rho, and type check and use them to type check E2 and get out a type tau 2 and in effect epsilon 2. Then we'll do the same thing using just the effect epsilon 1 for E3 to get out a type tau 3 and an effect epsilon 3. In order to actually assign one type to this if expression, we'll actually have to unify the types of each side. Now, ordinarily, you're probably familiar with rules, or hopefully you're familiar with rules where we sort of just constrain tau 2 and tau 3 to be the same. Here, that would be too strict because we actually want to be able to, as I mentioned before, combine the sets of loans that appear in reference types so that we can sort of broaden our analysis of ownership. And so that sort of unification on the bottom is what does that. Otherwise, if the types are not reference types, it just only works if they're exactly the same type. As a little bit of an aside, actually older versions or earlier versions of our semantics, the sort of formulation we had led us to that unification being impossible, or I believe impossible anyway. And so that's sort of how we got to this set of loans representation for regions. Okay. Now, we can assign a unified type to the expression, to the whole expression, and we can yield our effects in a sequence. And since we have to be conservative with our model of ownership in order to be sound, we actually have the effects epsilon 2 and epsilon 3 play out regardless of the value of E1. Right? So they both have to be true unconditionally, or they both have to be applied unconditionally. Now, I'd like to take a step back and give you all an idea of what exactly we model in Oxide. So we have user-defined structs, both the record kind and the tuple kind, which really, the tuple kind can be desugared to the record kind. We have enumerations. As we've already seen, we have branching, we have closures, and we have some simple pattern matching, which really means we have pattern matching with no nested patterns. So we can, of course, compile away nested patterns into sort of very repetitive applications of the function. And then there are a number of things, of course, that we don't model, the most notable of which are traits, which are sort of very complicated system on their own, and we hope to leave that for future work. Autoref and deref, which we view as sort of a necessary early compilation step because it's both local and syntax directed, as well as inferred temporaries, which again we view as a compilation step because it is local and syntax directed. And some of you who might be racketeers might recognize that as also meaning that it's macro expressible. So to this point, we've talked about Oxide as a single language. It's actually more apt to say that Oxide is a family of languages that build on one another with new features. The language you've seen to this point is called Oxide 0 and captures the semantics of safe Rust without any of the standard library features. Now, if you program in Rust, you might recognize that's probably not a super useful language on its own. So we actually build on it by adding individual standard library features to our semantics one at a time. So first, in Oxide 1, we add heap allocation. And we do this using the vec type. Anybody who's programmed in Rust might be thinking, well, why not the box type? Well, as it turns out, while a box can be viewed as a vector of size 1, box is not sufficient to implement vec alone. So we use vec, which can implement box, but the sort of reverse situation is not possible. Then in Oxide 2, we add shared memory using reference counted pointers, which if you're not familiar with the way they work, they're sort of, in essence, deferring the kinds of checks that we had statically for our immutable references or our shared references to runtime. And that allows us to write more complicated programs that use shared memory. Then in Oxide 3, we actually add interior mutability using the refcell type. And though it is not restricted to storing values only on the heap, it is otherwise analogous to ML's ref type. And finally, while our current goal is to formalize from Oxide 0 to Oxide 3, in the future we could extend our family of languages by adding the ability to spawn threads and communicate between them with channels. And of course, there's other possible extensions. And in fact, each level of this tower, as we've defined it, is defined by its new features increasing the expressive power of the language. In this case, we follow Matthias Fleisen in defining expressive power in terms of observational equivalence. So for those who are not familiar with observational equivalence, let's look at what it means for two programs, E1 and E2, to be observationally equivalent. So we say that two programs are observationally equivalent if, for all program context C, we can run E1 and E2 in the context, and either they both diverge, or they both evaluate down to a value, and that value is equal. Sorry.
All right.
Okay. At this point, I think a natural question asked might be, what's next? So in the immediate term, the formalization is still an ongoing work, and there's still a lot more work to do. And then in the future, we hope to be able to test our semantics by building a Rust to Oxide compiler and following the approach of Arjun Guha, Claudia Sappho, and Shiram Krishnamurthy in the essence of JavaScript, where they sort of use a real runtime and their built compiler to test that the semantics are equivalent. In our case, we care both about equivalence of the dynamic semantics and also the static semantics. So we want programs to type check in both or to not type check in both. And in the longer term, we hope that our semantics will enable a more rusty future, including formalized expressions to the language itself, including this very accurately depicted method of adding dependent types to Rust. A staple gun is definitely how you do that. We'd also like to use our semantics to define a framework for safe interoperation between languages, including OCaml and Belina. And actually, if any of you were at Amal's keynote, she talked a little bit about that. And then finally, we'd hope to be able to use our understanding of Rust that we're gaining from building the semantics to contribute to the ongoing effort to develop guidelines to explain to Rust programmers what unsafe code is safe to write. If you don't know, that's Nico, one of the Lang team leads for the Rust programming language, and he himself is wondering what unsafe code is safe to write. So now, at this point, we're just about done, but before I let you go, I want to quickly go over our running visualization again as a sort of high-level takeaway of our understanding of how Rust works. So we model ownership using fractional capabilities. Immutable loans split capabilities into pieces, while mutable loans keep them whole. When a loan ends, we return the capability to where it came from. Meanwhile, when we transfer ownership with a move, the capability is never returned. Finally, we define regions, or lifetimes, as a set of loans. This allows us to define attractable type-checking algorithms of Oxide. With all that covered, Ferris and I would like to thank you all for your time, and I'd be happy to answer any questions you might have.
Can you go back to the slide that had the wonderful role? Could you speak up? Yeah. Right, that one. So I was surprised that there's like no constraint on where the stick A is coming from. Does that not have to be bound somehow?
That's a good point. It makes it sort of cleaner to not have a bunch of side conditions, but it should be the case that stick A is not currently in L. It has to be fresh with respect to L. So L is the current set of valid rows, right? So it has to be.
Thanks.
Yeah.
So you were speaking about static semantics. We also have dynamic semantics and soundness or anything like that. Maybe I could.
So part of the project is definitely to develop the dynamic semantics and to prove soundness. We don't have a full completed soundness proof yet. But the main reason to talk about static semantics and not dynamic semantics is because really the static semantics of Rust is really nice.
And a quick question, when you move this capability from Y, does it mean that if you try to use Y in any way, it just doesn't type check?
Correct. Yeah, so you would get an error saying, well, there's a live mutable borrow, and well, in Rust at least we get the error. In Oxide you probably get a less nice error like, well, you actually just can't have the next rule.
Okay, fine, thanks.
Yep.
You had a tower of languages there.
Yep.
Do those represent your timeline, or are each of them useful separately from the others?
We feel that they're individually useful, particularly because you can sort of quarter off a domain, and perhaps a compiler could use them to say, like, well, perhaps a programmer could tell the compiler, I'm writing this program in Oxide 2 or Oxide 3, and you could actually use optimizations based on this knowledge. That's pretty speculative, but in principle should be possible, since observational equivalence is usually the way that we sort of guarantee the correctness of compiler functions. Okay. No more questions? Thanks, everybody.